Okay, good afternoon, everyone. Let's continue on with our discussion about semiconductors. Now, I posted an announcement yesterday about the quiz and the homework. So today's quiz Friday, just for this week, since this is the first one, I set it to all the way to Sunday. Okay, so there's no penalty. I mean, it's if you submit today or tomorrow or on Sunday, there's no penalty. Okay. You have all the way until Sunday night to get it done. But going forward from next week onwards, it'll just be Friday and then, one penalty extension till Saturday. Okay, that's from next week onwards. So this week is, well, you have almost 3 days to get that done. So get the homework done first for circuit analysis, and then the quiz, circuit analysis. So it's based on, as I said in the announcement, Ohm's law, KCL, KVL, current division, voltage division, and Thevenin Norton, which hopefully you are all still familiar with. Maybe, maybe not. I posted my 201 notes on the website, so they are available to students if they want. Also, my 201 lecture videos are there on the internet. So if you go through the playlists, you should be able to find it. If you just click on my name or the channel, you should be able to find those. Let me know if you can, or like I said, I could just post the link on the website itself. So I'll go ahead and do that. Okay. All right. So let's continue our discussion. That's what we were discussing in the other class also. 306, 321. All right. So we were talking here, right? Any questions before I begin on any of the material that we have covered so far? No questions? Okay. All right. So we are talking about the atomic structure of silicon, where each silicon atom bonds with its 4 neighboring atoms. They all share an electron each. So they all have 8 electrons in their outermost orbit. They form covalent bonds, strong bonds, and at absolute zero, none of the electrons are moving freely in the lattice structure. They're all frozen in place. They're all bonded together. As the temperature rises above 0 Kelvin, so absolute zero is 0 Kelvin, which is minus 273 degrees C. Some of the electrons acquire enough thermal energy that they are able to break free of their bonds. And so some electrons in that lattice structure acquire thermal energy. Did anyone have a question? Okay. All right. So they acquire enough energy that they now break free of their bonds and they're free to move around in the lattice structure. Okay. So they are now freely available for conduction. Okay. Let's see. Talked about the energy band gap and the energy band diagram. And then we talk about what happens when it moves out. Okay. So now they're freely available, but it's not as much or as many as metals. Metals have a lot of free electrons. They have no band gap whatsoever. Their band gaps actually overlap. Okay. So there's always free electrons available to conduct. Hence, they are good conductors of electricity. Silicon and other semiconductors, not so much. They have free electrons at room temperature, but not as much as metals. Okay. So now when an electron moves around, these are the ones that are available without any external energy source, except for thermal energy. Okay, except for the room temperature thermal energy. And so these free electrons are inherently present in the semiconductor material. And so this semiconductor material is known as an intrinsic semiconductor. Excuse me. Intrinsic semiconductor. So what happens when an electron moves out? It leaves behind an empty spot, right? These are the bonds. An electron moved out. And because an electron moved out, that atom, or the region around that atom, now has an extra positive charge. Okay, extra positive charge. So you have an electron, let's say you have these spots in the lattice structure. Students don't have to draw this. This is just small illustration. So let's say an electron is in every single spot in here, right? So an electron moves out and goes here. An electron moves out from here and goes here. Let's say it jumps into an empty spot. So there was an electron here, then moved away. It left behind an empty spot. And because it left behind an empty spot, there could be another electron some other place in the structure that could move into that spot. And so now, if the electrons are moving towards the right, the empty spot is moving at the exact same time. Well, not exact same time, but with a slight delay, that empty spot is moving towards the left. So electron jumps one spot to the right, then a second spot to the right. Now the empty spot is moving 1, 2, 3 spots towards the left. And so it behaves as if it's a particle in its own right. And so for purpose of analysis, long time ago, they decided we will treat it as a particle in its own right. And they named that particle as a hole. It literally is a hole because it's an empty spot in there in the lattice structure. But they call it as a hole. And the hole is treated or said to have positive charge. Okay. It's the physical absence of an electron, which leaves behind a net positive charge, but we treat it as a particle in its own right with a net positive charge. So we call it a hole. So we have electrons and we have holes. Electrons move of their own volition if they acquire enough energy. Holes move when the electrons are moving. So there's a slight delay. So something known as electron mobility, and there's something known as hole mobility. Essentially the speed, the velocity, and the of how much or how far these particles can move. Okay. So we have electrons and we have holes. And again, I'll give Professor Chuck Bland credit for the meme. And the answer is, of course, yes. If you lose an electron, you are positive. Okay, so intrinsic semiconductors are the semiconductors that have free electrons at room temperature. The intrinsic concentration, meaning the number of electrons is known as Ni. Number of electrons N, and the subscript of I notes that it's a intrinsic semiconductor, or the number of electrons present in that intrinsic semiconductor. So Ni. In general, for many equations, we simply use N for the number of electrons. And you can see the number for silicon is about 1.5 and 10 raised to 18 electrons per meter cube. Seems like a huge number, but again, it's not. Okay. If you apply some external electric field, those electrons are perhaps going to drift or move, but not enough to actually conduct some significant amount of current. So, oh, that shouldn't be here. Actually, no. I used the same meme. That meme shouldn't be in there. If we have only a certain amount of electrons, they are free to move about, but they are not sufficient enough to carry any appreciable amount of electric current or electrical energy. So what do? We want to increase the number of electrons, right? And how can we do that? If you want to increase the number of electrons in a semiconductor material, we introduce some other material in there. And here's what happens. We add external material into a semiconductor material. And because it is external to that material, to the intrinsic semiconductor, we call it an impurity, something that doesn't belong naturally in that semiconductor. Hence, we call it impurity. It is also known as, and first time I heard it, I couldn't believe it. It's called a dopant. We dope the intrinsic semiconductor with an impurity. Make it high. Make it fly high. But it's known as impurity dopant. Okay, so impurity dopant. So dopant or impurity dopant, all are just loosely used for any external material that is introduced into our intrinsic semiconductor material. Again, the goal is we have our semiconductor, we want to control the flow of current in there. We want to create some devices, we want to control the flow of current. But the number of electrons in that intrinsic material is not sufficient. So we want to add some in there. And that is something we can control. And that is the most important point. We can control the amount of impurity atoms that go into our silicon material. And thus, we can design devices with a very wide range of applications. Okay. So add impurities. All right, let's take a pause. Let me know if you have any questions so far. So if you are attending online, please feel free to speak up. There's a speaker here in the classroom. I will be able to hear your questions, but I will not be able to monitor chat windows. Any questions? So far, so good. Okay. So the difference between a conductor and a semiconductor when it comes to adding impurities is a metal already has lots of free electrons and the energy band gaps overlap, right? There's no energy band gap. The band gaps overlap. Okay, the energy bands overlap. So if you add more impurities in there, now the electrons that are freely moving around in the metal are now being interfered with the external impurities. So the electrons, the free electrons in a conductor are now encountering other externals. It's like a crowd of people that was free to move around was still manageable, but now you introduce more people in there. And so there's more traffic, more congestion. And so there's more difficulty for the electrons in a conductor to move around freely. And hence, because they cannot move around freely, they are not conducting electricity more freely, which means their resistance has increased. Does the physics make sense? Right? And so if you add impurity to a conductor, its resistance is going to increase. It decreases their conductivity. But with this, yes. To a certain extent, yes. So the question being asked is, depending on what the impurity is, does it always increase or decrease the resistance? The answer is, yeah, it depends on what the impurity is. We are simply talking about conductors, right? Right now. Okay, so well, semiconductors is different. For semiconductors, that's going to be the next point. If you add an impurity, now you're increasing the number of free carriers in there. So it decreases the resistance and increases the conductivity. So it's the opposite behavior of a conductor. Because now you're introducing more free electrons into the lattice structure. So for a conductor, it's opposite. You add more in there, it causes problems with the free electrons that are already present in there because they will collide with the other atoms and knocking the electrons off their path. And so it increases the resistance for conductors. But for a semiconductor, we do not have that many free electrons to begin with. So we add some more, and we are adding a whole bunch of electrons. Okay. And thus we can control and make our semiconductor into a conductor. And more importantly, we can control what the resistance of that conductor can be or should be. Okay. So silicon is from column 4 of the periodic table, 4 electrons in its outermost shell. Okay. If you introduce an element, if you introduce a dopant impurity element from column 5 of the periodic table, 4 of those 5 electrons will form a bond with the silicon atom. There's an extra 5th electron that is now free to move about. So every atom from column 5 that you introduce in there will form a bond. It will displace a silicon atom from its lattice structure and occupy that space. And once it occupies that space, it's going to share 4 of its electrons, which will form a strong covalent bond with the 4 neighboring silicon atoms. And then 1 extra electron is now free to move around. Does that make sense to everyone? Column 4 and then column 5, you add 5 in there. 4 plus 4 makes 8. You have 1 extra, 1 free to move around. Yes. That's the point that we are getting at right now. And so if you add something from a column 5 element, let's say here we are using arsenic, right? So if you use something from column 5, arsenic, phosphorus, it has 5 electrons in its outermost orbit. 4 of those 5 electrons will form bonds with 4 silicon atoms. So here it would be here with these 4 atoms. And now you have this extra electron. Actually, let me change. Let's use red. So 1 bond here, 1 here. And you have this extra electron that is now free to move around. So if you have this extra electron free to move around, now we have generated free charge carriers. So the amount of doping is huge. It's much larger than the intrinsic carrier concentration. The intrinsic carrier concentration typically is around 10 raised to 18. And the dose of the impurities is 10 raised to 19, 20, 21. Far higher, orders of magnitude higher than the intrinsic concentration. And so now you have this huge number of charge carriers, free number of electrons that are available to move around in that semiconductor material. And if you apply an external electric field, these electrons will move in response. So now if you have more electrons, you can freely conduct electricity, hence the resistance decreases. The opposition to the flow of electric current. Resistance is nothing but opposition to the flow of current. In this case, I mean, not in this case, current is basically the movement of electrons. So if the electrons are free to move around, it's a conductor. If they are not free to move around, then it's a insulator. Or basically quantity of electrons also. If you have very few electrons to move around, it's a insulator. If you have a large number of electrons free to move around, that's a conductor. So a semiconductor does not have sufficient number of electrons to move around, but we add some into them. And once we add that huge number or huge amount of electrons in there, or huge number of atoms in there, now we have a lot of free electrons free to move around. And because they are free to move around, they all have net negative charge. If you apply an external electric field, those electrons will move in response to that field. So now electric current is flowing in a material, whereas previously without the dopant impurity, it did not. So now resistance has, we can say resistance has decreased. Does that answer your question? Yeah. But this, we are adding an atom that has 5 electrons in its outermost shell. Okay. The net charge in that doped material is still neutral, because the electron is moving around. But that electron also has an accompanying proton that is bound in the nucleus of that dopant impurity atom. So if you have, let's say in this case, it's arsenic, if it's losing one of its electrons to move around, there's a net positive charge that is still held in the nucleus of that arsenic atom. So overall charge is still balanced. Overall charge is still 0. Okay, that's a critical point. It is not a charged device. The overall charge in that doped material is still 0. And so you have one extra electron. And which is balanced by proton in the nucleus. The dosage levels are typically 10⁻⁹ to 10⁻²2 atoms per centimeter cube. A huge number of atoms. Okay. All right, any questions? Let's take a pause. Yes. Oh, atoms per centimeter cube. So one tiny cubic centimeter is flooded with 10⁻20 atoms of the dopant dopant impurity. Yes.
Do you have like a rough percentage number of what that would be, the ratio of those to like semiconductors?
Ratio of dose to semiconductor, meaning the for silicon, it was 10⁻18. So it's more than that. More than that, yeah. So that 10. So the question being asked was, what is the intrinsic value? So the answer is 10⁻18 atoms per centimeter cube. And so also, the that intrinsic concentration sometimes, well, actually, you know what? Let's not veer into that topic for now. Let's just leave it at that. We'll talk about it in the future. So we have the intrinsic number of atoms, and then we have extrinsic. So we add some into our material, and now we have created an extrinsic semiconductor. And because it has free electrons to move around, we call it a N-type semiconductor. N for negative. So we have created an N-type semiconductor. Okay, N-type semiconductor. Again, overall charge is still neutral. Okay, overall charge is still neutral. All right, so this is column 5. What happens if we introduce an element from column 3? Column 3 has 3 elements in the outermost orbit. So now we have the absence of a charge or an absence of an electron. And so if you take a column 3 element, such as boron or gallium, three of those electrons, that shouldn't be arsenic. That should be, let's just use boron. And that shouldn't be negative. So it's boron, you have 3 electrons in the outermost orbit, valence shell, and those 3 of them will bond with 3 neighboring silicon atoms, but 1 bond will be left open. Right? 1 bond will be left open. So there is a hole or an empty spot in there. And so that's a net positive charge in there. And so now we have created a P-type semiconductor. Okay, so column 5 impurities, 1 extra electron. Column 3 impurities, 1 less electron. So we have 1 positive charge. And hence, if you flood it with like 10 raised to 20 atoms from column 3, you have that many net positive charges. Overall charge is still, again, neutral. Okay, because every electron is still balanced out by the proton. So overall charge is neutral. All right. So this is the extent of the discussion we'll do for the semiconductor physics. Again, especially as non-E majors, all you'll be doing is you'll be taking, it's important to know the physics, but then you need to know about circuits using these devices. Okay, so these are just the basic fundamentals. So we don't go into like the detailed equations, you know, drift and velocity and mobility and electric field depth and stuff like that. Yes. Thermal energy. Yes. So the question being asked was about free electrons in intrinsic semiconductors, and they are acquired because of thermal energy. So we start, you know, the explanation starts from absolute zero, where everything's frozen, nothing ever, you know, there's no energy whatsoever. But then as it rises from absolute zero all the way to room temperature, now it has acquired thermal energy, and so electrons are free to move around. So now we have the P-type and the N-type semiconductors. If they are brought in close contact, this is not actually what happens in real life, obviously. This is a 2-dimensional cross section. Actually, not a cross section. It's two-dimensional illustration. It's not a cross section. Okay. So you have a p-type material and an n-type material, and you bring them in close contact. What happens? Well, what we obtain is a p-n junction. P-n junction. And when you bring them in close contact, at the junction itself, if you have an electron and it sees an empty spot, it's going to jump into that empty spot. So when an electron jumps into an empty spot, we call this process as recombination. Recombination. Okay. And when it recombines, meaning an electron jumps into an empty spot, a hole, and a hole combines with electrons, both is physically both is exactly the same thing. Electron jumps into an empty spot, right? It's moving from spot to spot. That's called recombination, and it takes place all the time. So when recombination takes place, there's some energy that is expelled. But more importantly, this is what happens. Because of recombination, those charges disappear. You have an electron that had a negative charge, and you have a hole that had a positive charge. When the negative charge moves into that empty spot, one negative charge disappears and one positive charge disappears. And so there is a region that develops right here at the junction. And this region is completely devoid or depleted of all charges. And hence, this region is known as the depletion region. Okay. It is devoid of charges. It is depleted of all charges. Hence, it is known as the depletion region. Depletion region. There's quite a few more things that happen here. There's just giving you a little bit more information. There's an electric field that is generated. That electric field gives rise to a voltage that is opposite of the polarity of the diodes. I mean, it's not diodes, of the p-n n-type semiconductor, and it reaches a level of charge neutrality. And so there is a distance to which this depletion region extends into both the p and the n-type material. Okay, and that is illustrated right here. Actually, not that big, right here. Okay, and at that point, it stops moving. The electrons in the holes stop moving into the opposite territory. Okay. Now, in the E major classes, we go in depth. We talk about the equations that are, that are required to calculate for the movement. We calculate. There are equations that we use to calculate the voltage across that junction. Okay. So because of this barrier right here, if you want to conduct electricity through this barrier to this junction, some of that energy is consumed in overcoming this barrier right here. And that is defined as the built-in junction potential. Okay. So this is a barrier which needs to be overcome. And is known as the built-in junction potential. And this is similar. It's kind of like a material property. Okay, for silicon, this voltage is typically taken as 0.6 to 0.7 volts. Depending on the textbook, depending on the author, some authors like to use 0.6 volts, some like to use 0.7 volts. So this is the amount of voltage that is required to be applied to a silicon PN junction before it even begins to conduct current. Remember, last class I stated, we have linear devices and these are non-linear devices. You keep on increasing the voltage, but the current does not increase linearly with that voltage. And so if you apply 0.2 volts to a silicon diode, current would be 0 because the junction potential is like this depletion region is a barrier between the two P and N type semiconductors. This barrier needs to be overcome, and that brings the holes and electrons into much closer contact. The depletion region shrinks, and beyond 0.6 or 0.7 volts, shrinks down completely to 0. The holes and electrons are free to cross over from both sides, and free conduction of electricity takes place. For germanium diodes, it is about 0.2 or 0.3 volts. Typically, you would see 0.6 or 0.6 and 0.2 volts. Okay, this is the voltage that is required to overcome that barrier. When holes and electrons move, through a circuit, thermal energy is expended. So these devices get hot. Okay, these devices get hot. If we create a two-terminal device using just a P and an N type material, we obtain what is known as a PN junction diode. Again, the name or the nomenclature is derived from the vacuum tube diodes, which had actual electrodes in them. Remember, vacuum tube diode had an anode and a cathode, 2 electrodes in there, diode, 2 electrodes. So when they created the solid state version, they carried over the nomenclature and it became a solid state diode. The symbol for a diode is this triangle with this vertical line right at the arrowhead. That line signifies the cathode, and the tail end of the arrow is the anode. Anode is where the P-type silicon is, and cathode is the N-type silicon. They're also referred to as A and K. A and K. On an actual silicon diode, sorry, for that matter, not just silicon diode, for an actual diode, it is marked with a band. If you look in your lab kits, you will see a small device with a black coating and a gray silver band. That's an actual diode right there. Okay. So that band indicates it's a cathode. There are other kinds of diodes, different kinds of plastic packaging, transparent packaging, where it would be a different color band, like an orange or red color band. But that band that goes around that small, tiny cylinder indicates that terminal is the cathode. Okay. Positive here, negative here. When holes and electrons are moving through these devices, thermal energy is expended, devices become hot. There are other semiconductors which are created from multiple compounds. So you can have gallium arsenide, gallium nitride. If you combine 2 elements from column 3 and column 5 of the periodic table, you now have what is known as a compound semiconductor. And compound semiconductors behave a little bit differently. Nowadays, you might be hearing about gallium nitride chargers, right? Previously, the circuits were built out of silicon. Now, some of the circuit components are made out of gallium nitride, column 3 and 5. It's gallium nitride is because it's a compound semiconductor. And many of these compound semiconductors we'll talk about this compound semiconductors. Column 3 plus 5. Some examples are gallium nitride, gallium and arsenic, gallium arsenide, there are gallium phosphide. But gallium arsenide is a very popular compound semiconductor because instead of, well, it does dissipate heat, but most of its energy is dissipated as light, as photons. And if you create a diode, a PN junction diode from a compound semiconductor like gallium arsenide, you get what is known as a light emitting diode, or LEDs. So LEDs, that's the reason why it doesn't get as hot as a filament light bulb. Filament light bulb is based on resistance. The filament in the light bulb resists or opposes the flow of current. Most of it is dissipated as light, but a lot of it is also dissipated as heat. So old filament light bulbs were highly inefficient. They are dissipating light, but also dissipating heat at the same time. LEDs dissipate most of their energy as light and just a little bit as heat. They too get hot. Every electrical and electronic device gets hot because there is a thermal energy that is expended. But in an LED, it's not as much as a filament light bulb, hence more efficient. Okay, any questions so far? Still have about 8 minutes. Yes. Gallium arsenide. I think even phosphide, I think also has, let me see, phosphide, maybe not, but definitely gallium arsenide. Yes. So question being asked is about the color. And yes, so depending on the dopant impurity that we introduce into the semiconductor, the wavelength of the light changes and hence the color changes. Good question. Yes. So the question being asked is, why do we only have this depletion region, right? It's a very good question. And that is the one thing I said that we won't go into too much detail in the physics. So when the when the positive, the holes from the positive side from the p-type material cross over into the junction, and the electrons from the n-type material cross over into the junction, the assumption would be that they would keep crossing. Well, the reason they cross is because there's a charge imbalance. Holes are attracted to electrons, positive and negative charges attract. So the assumption would be it just keep continuing until the charges are all neutralized, right? But the reason it doesn't happen is because when they cross over and recombination occurs, an electric field is established. And that electric field that is established because of this recombination phenomena establishes or gives rise to a voltage. And that voltage in turn gives rise to another electric field that is in direct opposition to the holes and the electrons on either side of the junction. So the movement gives rise to an electric field. That electric field opposes the movement of, or the further movement of holes and electrons. So depending on the material, at a certain point, that barrier, right now this is a junction, but the barrier is established, but the barrier then stabilizes. And that's the best word to put it. So barrier stabilizes because of the electric field that arises because of the movement of these holes and electrons. Yes. There are some left, but not a whole lot. It's almost completely devoid of electricity. Yes. For silicon, yes. So when the barrier stabilizes for silicon, it's around 0.6, 0.7 volts, and for germanium, it's around 0.2 to 0.3 volts, meaning that's the voltage that is required to overcome that potential. Yes. Same question? Okay. That was a good question. But I am teaching E306 right before this one. So if any one of you are interested in learning more in depth or want to go through the equations, feel free to come in early. We'll be talking about those in depth. Okay, forward bias and reverse bias. If we take a PN junction diode, right, we have a P-type and an N-type, anode and cathode. And this is something that you'll have to get used to very, very quickly, right? So you have P-type material, positive anode. N-type material, negative cathode. If the anode is at a higher potential than the cathode, then we say that the diode is forward bias. Okay. We say that the diode is forward bias. So you have P-type material. You have lots of holes here. You have lots of electrons here. What happens? Anode is higher potential, meaning it's at a positive level. Cathode is at lower potential, so negative level, negative charges, right? Depending for the source. So if that's the case, then the holes and the electrons are repelled away from that source. So they're moving in this direction. And the electrons are moving in this direction. So what happens? In the depletion region, the charges have now replaced each other, right? It's recombined and so it's opposite. So you have holes in the N-type material and you have electrons in the P-type material. But now, because you're forcing the holes and the electrons away because of the external source, the junction starts to shrink. The junction shrinks and holes and electrons are able to cross over the junction. So they have enough energy, cross over the junction. And because electrons are now free to move, charge is being conducted. Movement of charge is nothing but current, I. So electrons are moving in this direction. Which direction is current flowing? Coming down. So I is coming down. If I extend this arrow for a source which is supplying energy, goes from minus to plus, right? It all ties back to the beginning. A source always supplies energy, meaning currents always go from minus to plus. And so in this case, electrons are flowing in the other direction, currents flowing through the circuit. So your device is now conducting. Okay, I think we are almost out of time. We just have a few more seconds left. So I'm quickly going to talk about reverse bias. I'll go more in depth on all of this on Monday also. But reverse bias is the exact opposite. If you apply negative to P-type and positive to N-type, then the depletion region is now expanding because the holes and electrons are being pulled away from the junction. And because they're being pulled away from the junction, it's now being expanded. So there is no current flow whatsoever. There are no holes and electrons that are crossing over the junction. It's just opening, behaving like an open circuit. Okay, so the depletion region expands. And no current flow takes place. And so forward bias, it behaves like an open gate. Reverse bias, it behaves like a closed gate. Forward bias is free current flow. Reverse bias is no current flow. And that is where we'll end class today. So, tons of things to think about. On Pearson, on Mastering Engineering in Pearson, does an e-text show up? E-text, the textbook. Is there a link for an e-text? Or does it ask you to purchase it? Okay, yeah. That's what I thought. I we recently did a purchase for another one of our classes, the E major classes, and let me stop recording first. Like